to talk about a topic that's impossible to talk about in this time. So what I'll do is first try to convince you that there is something to trying to use statistical models to model things that change over time series, especially multivariate time series. All kinds of problems emerge when you try to do this, and this has to do with a lot of statistical assumptions that you have to make for these models to fit. So that's why this is called when n is 1. That's another thing. I'm going to talk about single subject data sets, and t is many, t is time. So model 3, you can already see it's in scary quotes. So that means that I actually do not believe there are no models, as you might have guessed from the question. What I mean is no models or parameters are being estimated from data. It's basically a descriptive analysis that I'm going to talk about. All right. If you really want to know everything about the stuff that I'm going to show you, you can look in these papers. And there everything is explained, and they come with R code and all those kind of things. So what are we talking about? What you see here on the left is a multivariate time series. This is from an experiment done in one person who it's a double-blind experiment, which means that the participant as well as his doctor and the experimenters were unaware when the dosage of his antidepressant was gradually reduced. So this was a depressed patient, and at some point, unbeknownst when, they started to reduce the amount of antidepressants. And this patient recorded 239 days, I think, yeah. And sometimes 10 times a day, he asked questions. So what you see here is questions like, how do you feel today? How's depression? And the goal of this study was, so this is not my study, but it's Wiekers and Groot, beautiful data set, which is very often used to test all kinds of things about time series analysis. The goal was to find early warning signals for the critical transition. And what happened at some point, day 127, there was a relapse into depression. What you see here is the depression scale, which was measured weekly, so it's less frequently. And you can see that, this is the symptom severity. So, at some point, the severity was just too much, and then they decided to stop the experiment also. So this is a period where no data was collected. And then they started with medication, because you can see that it didn't really help. So there was a transition from one state, which was kind of non-depressed, or at least medicated non-depressed, into a depressed state. And you can sort of think about that. So this is all coming from, let's say, complexity science, the idea that we can study the changes of behavioral modes, you would study phase transitions in, for example, if you boil water, right? You increase the temperature, and then you get water from liquid state into a gaseous state. The same thing you could think about that in going from a healthy state into a depressed state. And there are all kinds of interesting phenomena that occur around these transitions. And one of them is critical slowing down and critical fluctuations. And what they did in the original paper was they tried to look at those things. So they looked at autocorrelation in the data, which had to increase, and the variance. So, beautiful data set. I have some problems with the way that this was analyzed. So I'm going to talk about a number of those problems. And the first is these assumptions you need to make in order to be able to fit statistical models. The second one is the data aggregation. You can imagine with this data set, what are you going to take? Are you going to do everything separate, or are you going to average? And well, they made some decisions there, which I also have some questions about. Segmentation, also what happens is people start to chop up the time, right? Because it's 239 days. And then, start to analyze separate epochs of the data, which is also not something I suggest to do. And the last one is a little bit more technical maybe, but most of the analysis and the models that are used, so also these like symptom network models, they use lag one autocorrelations, which means that they analyze the time series as if the only thing that's important is, let's say, one time step. In this case, it's like days, right? If you aggregate at the day level, which means that they allow correlations between two observations only that last only a day. But we'll see that this is much more complex. Oh yeah, this is something that I will not talk about, which has to do with experience sampling or ecological momentary assessment. If you ask people to rate your internal state, it has all kinds of measurement problems, but I'm not going to talk about it. Okay, so you might know this from Andy Field's book, right? Assumptions about the tests, parametric tests, are additivity and linearity, normality of something or another, homogeneity and variance, and independence. I think these are kind of familiar, right? So that's what you need to have before you can run your analysis. But what about statistical models for time series? Well, actually, there we have, and I think actually these assumptions are also derived from one of Einstein's papers that he published, I think 4 papers for which he would have had the Nobel Prize in 1905. But what he was studying, it was the movements of dust particles in water, which create a very random looking path. And he made a formal model for that behavior, which we now know as Brownian motion or random walks. And what does he say? He says you need to have independence of individual particles. Yeah, check. Existence of a sufficiently small time scale beyond which individual displacements are statistically independent. The lag one autocorrelation that is used in these models, that's where this is coming from. So we can accept a small time scale where we have correlations, but it shouldn't exist on longer time scales. And the third one is the property that the particle displacement during this time scale corresponds to a typical mean-free path distributed symmetrically in positive or negative directions. Normality of something or another, right? So if you have those things, those assumptions, and your object of measurement or your system that you're studying corresponds to that. Oh, I don't know if it's visible, but you can see this trajectory in the top corner there. Then you have an ergodic system. And if you have an ergodic system, it's very neat because what you basically can do is you can take a whole bunch of observations of different states of this system. Let's say a sample of people from the population, random sample, and observe them once, and then the distribution of the values that you find would be exactly the same as if you would observe the same system, let's say 100 times or 1,000 times. So the time average and the space average are exactly the same, expected to be the same given infinite time, if you are dealing with ergodicity. And actually, yeah, these assumptions here are basically the assumptions you need for fitting statistical models. Taken together, this is sometimes called the memorylessness property, which means if you take a time series, there is no memory for initial conditions, so it doesn't really matter where the system started. It doesn't influence the outcome, and no after effects of any interactions along the way. So yeah, basically a random process. Okay. Well, if we do measurements on people, Lord and Novick already figured out that then you run into a problem because there is always an after effect of the fact that you've measured someone, right? So the test-retest idea, and they call this brainwashing. So you can only do this if you wash the person's brain, and then you would follow the assumptions. So the question is, does a sufficiently small time scale beyond which individual self-reports are statistically independent exist? Well, here is, you can read it, but it doesn't matter. These are all questions from this large data set that I just showed you, right? From this double-blind experiment. In the columns, you see all kinds of tests that are testing these assumptions. So what do we find in these time series? All kinds of regime shifts, non-stationarity, non-homogeneity of variance, lots of memories, lots of long-range correlations, values that keep recurring, lots of patterns in the data, a non-stationary autocorrelation function, sensitive dependence on initial conditions that's kind of the idea of violates the idea of no memory for initial conditions. So if you want to read about that, that's in this paper. So that's a problem, I think. So that's a problem for fitting statistical models to these data. So this is about from the paper, from the original paper. And here you see that they calculated the goal was to be able to predict this shift here, right? Shifted to the depressive state. And they used a sliding window analysis of 30 days and calculated the autocorrelation, and yeah, it goes up. Before, let's say, but it also goes down, and but that's why they failed it, I think. And variance also went up. So that was their conclusion was, yes, we've seen all the signs of phase transition, of critical slowing down, and that was sort of their conclusion. But the question is, of course, what did they use to calculate these things? They also did some network analysis. It turns out this data set was transformed by doing PCA, principal component analysis. I think you should not treat them as factors, but they named the components. And then there was worry and suspicion. That was just one of these variables. So, and the PCA was done on a subset of 11 variables. Then they created this kind of network, and then it turns out that these things are calculated on then just the average or sum of all these components. Yeah, that's becomes problematic for me, because now I do not know anymore what is going on. Why is this going up? Is it one variable? Is it the PCA? Is it so I think this is well, could be a problematic. I'm not saying that it is, but it could be problematic. And what they also did was the segmentation of segregation. So chop the time series up in parts and then do your network analysis. So this is a network analysis. This is based on these vector autoregression. I don't know if you know that technique, but that's kind of simultaneous regression technique where you can estimate temporal correlations. And yeah, they see that according to their hypotheses that there were some differences. They have hypothesized different connections emerging around this shift. Okay, so last one, that's the lag one, autocorrelation. So vector autoregression is this technique. I think comes from economical science, but it allows you to simultaneously estimate these correlations, and these types of networks are very, we see them very often, but not recently. So this year, a review paper came out. So there in the authors, you can see those are all the important people who have done beautiful work with figuring out this method of symptom networks. But what do they recommend? There are methodological and practical challenges that hamper moving from theory to clinical research. And second, these challenges include, for example, the use of nodes with different timescales. So that's exactly what I was pointing out. What you see here is basically the associations that exist in the data one day apart. But we know, well, I've shown you, if you believe me at least, that there are many, many more complex correlations in these data. So what can we do? Can we do something about this? And can we also do something about potentially using this in practice. Because what is the idea? If you can find these early warning signals, if you monitor a patient, yeah, you might be able to do something, right? If you're noticing that there's critical slowing down, you might want to intervene. Or you do something that is more preventive, maybe. So, the goal for the next part, yeah, that's fine, will be to present something that could be used potentially in practice. And it's based on the same data set. And that has some consequences. So if you want to do this, so make it possible to implement it, yeah, we have to think not statistics, at least not in the traditional sense. We will just have data from one person coming in. Could be a lot of data, of course, but yeah, it's unlikely we can fit models and then make use of the fact that we have many people. The fact that we're probably dealing with non-ergodicity also means that we'll have to use complexity methods or maybe descriptive methods or descriptive analysis, maybe you might call it. We need to be able to do a real-time analysis as data come in. And so this is the no time travel rule. So what you very often see in these studies is that, in these time series studies, is that they have collected all the data and then do their analysis. Basically, they make use of things that have not yet occurred, right? And that's not what you want if you are working in a practice. Then data is just coming in every day, so you can make use of those things. So in our analysis, I need to think about that and basically don't use data points from the future. Let's say no time travel. And yeah, I'll skip this one. And maybe I can have time to talk a little bit about this, because we do, of course, want to know, are we just looking at noise, or we have to have some kind of evaluation of the accuracy or precision. So what is this analysis that I'm talking about? It's an analysis based on recurrence quantification analysis. Here you see two stories. They're exactly equally long, and this was written by kids. They got a picture, and then you had to write something. Well, the content doesn't really matter, but if you know Dutch and you read this quickly, you will notice that there's a slight quality difference there. So they have about the same mean length of utterance, same number of words. And so what you can do is you can change this into a time series, just give a unique value to each word as it comes up. You can get something like this. And what is recurrence quantification analysis? It's very simply plotting the time series against itself and noting, okay, this word occurs now, doesn't occur sometime in the future. So you get a symmetrical plot here, and dots that indicate whether something is recurring or not. And you can find line structures, which means that there's a pattern that is recurring. So 3 words in a row occur at some point, but then are repeated at some other point. And yeah, you can do all kinds of calculations. Count how many recurrent points there are, how many points are on a line, how many points on a vertical line. These things have all meanings, but we're not going to talk about it today, because what you can also do is this. You can create a network from these data. Once you have this matrix, you can create a network. And so imagine that this is time, right? So all the nodes are actually time points. And what you do is you create an edge, so a connection, whenever a value is recurring. So this was story 1, this was story 2. You can already see there's much more repetition in this story. Right? Many more edges. Okay, so back to our data set. How do we do this for continuous data? Well, and this is where the no model scary quotes come in. What if we assume that let's say were all kinds of questions about mood, 12 to be precise. What if these values that we have for each day, they all represent a state of the system, a state of this person that is related to mood. So what you have then is a 12-dimensional state space for mood, right? So this is assuming that what you are recording here is actually good, right? That's really an actual good measurement of the state. What you can do then is think about it like this. So this is one state occurred time the day 10, 12 numbers. These are all answers to these questions. At 110, we also have a 12 tuple. And yeah, if you have those coordinates, you can calculate the distance. What you see here are those 12 time series and how far apart they basically are. So you can imagine that states that are close together might be recurring states. States that are far apart are non-recurring states. They can recur at different times. They can recur in different sequences. So you can do exactly the same thing as with the words by picking a kind of a threshold here that decides, what do we call recurring? It's kind of a parameter that you need to decide on. And there's also a recurrence time. So suppose this is indeed a recurring point. Yeah, you can also get at how long does it take before this state recurs. So so far we've not done anything in terms of statistics, right? We've not estimated anything. We've just calculated distances, basically. But I do concede that this is, of course, a kind of model, because what we're assuming is that we can capture this as a state space, basically. So if you then pick the distance beyond which you say, okay, this is the same, below which, you can get something like this. So this would be a recurrence plot with 5% recurrent points. You could also say, okay, I still want to be able to distinguish these points because they might have different recurrence times, for example. So you can also make them weighted. In this case, it's weighted by recurrence time, which means that some recurring points will have a value that's indicating this doesn't recur until a very long time, or this will recur very shortly. So once you have that, you can create a network. So this would be the mood network. And you can see here I made different colors represent the different phases in the experiment. And yeah, once you have this, you can use all your network measures, like centrality of the nodes, edge density, shortest path. I don't know if you know anything about network analysis, but those are the regular things that you would do if you have a network. And what is interesting is that you have time is still represented here. And in principle, all the different dimensions, all the 12 different dimensions, are still accessible in the sense that if I want to know for this point what the exact coordinates are, I can just look it up because I have those values. So we've not aggregated anything yet. And we've maintained the time. So how do we, in the analysis, how do we take the no time travel rule? Well, you can create a directed network, which means that, so at time point 1, we don't know anything, right, about what's going to happen. But time point 2 might be recurring version of time point 1. Then time point 2 will get an arrow that points to 1. But it means that at 1, I don't know anything. I'm not receiving anything. And in network terms, basically, you say, we're only going to analyze the out degree of the network. And that way, it's kind of a cumulative analysis. So there were like 70 variables, right? So I made one for mood, for physical fitness, self-esteem, mental unrest, sleep. And so let's say 6 subsystems or sub-state spaces. We can create networks from them and calculate all these network measures. This probably doesn't mean anything to you, so I'll quickly skip this. But what you get then is a kind of hint at how accessible are the different states and how often do they occur, and do they occur in different patterns. That's not all. Because you can also do something called a multiplex recurrence networks. So here you see all the individual networks, and then you can basically say, oh, but this is actually a giant network because they have all been simultaneously measured, right? So they've been measured at the same point in time. So you can put them all in one large network and, for example, evaluate what the relationships are between the different layers. Lots of different options to do that. You can look at, do they have the same structure in the node? So are the connections to each node similar? Do they share the same edges? Do they share the same connections? But all is just counting. It's basically all descriptive statistics. But it does give you interesting information. And I'll just skip some things here. Oh, maybe this one. So what you see here is, this is the analysis from the original paper. You see the variance going up, right, and the autocorrelation, and around here is this critical transition. But if you look in this symptom severity time series, you can see there are actually many more transitions, and these measures here, those are the measures from the multiplex network. So it's also windowed analysis of some of these connection values. What you can see is in these red and green bands, you see a lot of peaks occurring there, right? And that is, to us at least, is an indication of that a shift might be occurring in the future. And you'll see that very often these indeed align with the shifts, which are just not possible here. This is just very general. So what you would like to do is make some kind of test that tells you how well you have been doing this. And that would be, I think, for another talk. Just I'll stop at this this last slide. Because what you see here, this is one of those subsystems, let's say, and what you see here are the states that are recurring. You can sort of interpret them, right? So this was an uneventful day or a nice day, and so it's high on uneventful and low on nice day, and there we have a phase that is kind of a little bit different. And based on this information, you can create a kind of a transition matrix, transition network, which tells you how likely it is that the person will move into a particular phase. And in this case, the phase 1 would be the depressed state. I think I'll stop here. Yeah. Lots of information, but remember, can I go back? Yeah. This is the take-home message. First analyze and then aggregate. Thank you.